прошлый раз окончилась физическая часть рассказа, а теперь пошла математическая, в которой я честно признаю, что чувствую себя более уверенно, чем предыдущие 2 часа.
Слушатели могут признаться к вам же.
Вот. Поэтому, значит, в общем, я теперь встаю на позицию математика, который открыл вот книжку Фейнмана «Статистическая механика». Может быть, вы уже устали от цитат из великих людей за предыдущую лекцию, но я предусмотрел тоже одну цитату. И прочитал, значит, математик прочитал первую фразу. Основной принцип равновесной статистической механики состоит в следующем. Если равновесная система может находиться в одном из n состояний, то вероятность того, что она находится в состоянии с энергией E, равна 1 поделить на z, E в степени минус E поделить на kt, где z равна сумма E в степени минус EI поделить на kt. Вот. Значит, я списал первую фразу из Фейнмана, а дальше предположим, что, значит, дело не пошло. Возникли какие-то другие дела, и на этом чтение книжки Фейнмана прекратилось. Что будет делать математик дальше? Ну, дальше нужно придумать какую-нибудь систему и какую-нибудь энергию. Ну, допустим, самая простая система, допустим, это состояние, например. Состояние это действительная прямая, а энергия, например, равна x квадрат пополам. Пополам будет проще, ну, не знаю.
Я не сумел представить букву, которая у e в степени минус на второй строчке.
Вот здесь вот, да. Это буква И, но это сумма по состояниям, и это состояние.
Там Е, которая стоит не отсюда написано.
А вот это вот. Да, это энергия итого состояния. Когда состояний бесконечно много, вместо суммы будет интеграл. Ну вот это самый простой пример. Вот там энергия пружинки, о которой нам только что рассказывали. Значит, поэтому нам нужно сразу же посчитать интеграл e в степени минус, ну давайте я сразу поставлю константу бета, x квадрат пополам dx. Да. Ага, хорошо. Ну тогда вопрос, как в прошлый раз. Если, значит, если люди, которым не понравится, если я буду говорить по-английски? Людей нет. Окей, then I switch into English. So this integral, I think we computed it last time. It is equal to square root of square root of 2 pi divided by beta. I'm not sure if I have to compute it again. No. I think it's okay. I think you will believe me. So exercise for those who don't know how to do that. Okay, so now we have the expression for the partition function, and if we take the logarithm, we obtain the expression for the free energy. But now we would like to compute, for example, the expectation values of some function. So definition. The expectation value of f of x is equal to the integral of f of x e to the power minus beta x squared over 2 divided by z. This is a very natural definition. This is really the expectation value of f of x in the usual sense. So now I can ask myself, for example, what is the expectation value of x to the power k? And if I know how to do that, well, the problem will be more or less completely solved, because any other function can be decomposed into a Taylor series at the origin. So if we know the expectation values of x to the power k, we more or less know the expectation value of everything. Okay, so let us start with The expectation value of 1 is by definition z over z, so this is 1. Which is lucky, because the expectation value of 1 could be nothing else. The expectation value of x to an odd power is equal to 0 because we are integrating an odd function in the numerator. So the integral of an odd function is equal to 0. Now let me compute the expectation value of x squared. This is probably the computation. Yeah. Shall I do that? Yeah, I think I'll. Okay, so let me compute the integral of x squared e to the power minus beta x squared over 2 dx. So we integrated by parts. By parts. This is equal to the integral. Let me see how I do that. X over beta d e to the power minus beta x squared over 2. Right? Because if you compute the derivative of that, you keep the exponential and there is minus beta x in addition. So minus beta x times minus x over beta is precisely x squared. So this is equal to the difference of values of x over beta e to the power minus beta x squared over 2 between minus infinity and plus infinity plus the integral of e to the power minus beta x squared over 2 dx over beta. Okay, so this is this is equal to 0 because if we go to minus or plus infinity, this exponential kills everything else and tends to 0. And this is equal to 1 over beta times z. The only difference is this beta in the denominator. Otherwise, it is precisely the definition of z. So the expectation value of x squared is equal to 1 over beta. Which is also something very well known, because this function is actually the normal distribution with variance 1 over beta. So what I have just found is the variance of this distribution. Okay, and then now there is the question of x to the power 2k, and I will go back to this later. Actually, you can compute this in the same way I computed it here by induction, by performing integration by parts and going from x to the power 2k to x to the power 2k minus 2. But I prefer to give you the general formula and then come back to this case as an example.
So, Dima, are we expected to forget all the physics we heard about, or we can feel somehow this expectation value? Does it mean that something?
I think you can forget everything for at present. I will make some references to it later, but it will be more or less general remarks. Then. Okay, well, you'll see later what kind of remarks I'm going to do, but I won't really use anything from the last 2 lectures. Okay, so now let us go from r to the n. And instead of x squared, I will take, well, instead of beta x squared, I'm going to take any positive definite quadratic form. So let's be a symmetric positive definite n by n matrix. Then I define z as the integral over Rn of e to the power minus 1/2 bx x dnx. Okay, dnx stands for dx1 dxn. So this integral is equal to 2 pi to the power n over 2 divided by the square root of the determinant of b. Let me prove that. Proof of this. Okay, this is a very easy theorem if we assume that B is a diagonal matrix. And actually we can always, by a change of coordinates, by a change of basis, we can always transform B into a diagonal matrix. So let us take, basis change. Change matrix P of determinant 1, because I don't want it to change the volume. It would be an unnecessary complication. Such that, so for a quadratic form, we take P times B times the transpose of P. And this is a well-known theorem, well, probably you know it from school, that you can always find a matrix P such that this is a diagonal matrix. Okay, so then Z is equal to e to the power minus 1/2 P transpose BP x scalar x dnx equal to the integral of e to the power minus 1/2 bpx px dnx. Okay, move the transpose matrix from here to here. And this is equal now, if I call this vector y, since P does not change the volume, this is simply equal to minus 1/2 dy dny. Yeah, I should have written it from the other way around, actually. This last line is the definition of Z. And then I can go back to this computation, and this is just the matrix beta. Okay, so once we have performed this change of basis, what we obtain actually is the normal distribution independent for each coordinate. If here we have a diagonal matrix, it means that actually we have a normal distribution in variable x1, an independent normal distribution in variable x2, an independent normal distribution in variable xn, and this integral is decomposed into a product of n independent integrals. So this is how we obtain this. And the determinant of b is equal to beta 1.
I know we're told it because we had square root before, yeah?
Yes. Yeah. Before it was square root of 2 pi divided by square root of beta, and now we just multiply it for all betas and we obtain this. Maybe I'll take a So now, as before, we would like to compute the expectation values of some polynomials of x.
Well, x is a point in Rn.
Yes. Polynomial in x1, xn. So again, as before, we have, well, the expectation value of 1 is still 1. The expectation value of an odd polynomial is equal to 0. For exactly the same reason, if we integrate an odd function, well, the integral vanishes. Now, if you do not know the answer, maybe you can try to guess what is the expectation value of xi, xj. This is the first non-trivial case. It is an even polynomial of degree 2. So the answer is yeah? What is your guess? No, there is no 2 pi's. Last time, maybe I recall that last time we had the expectation value of x squared was 1 over beta.
Then it should be 1 divided by square root of beta I beta.
No, but this is okay. But here I do not assume that B is a diagonal matrix. B is just any symmetric matrix. Betas are, what is beta I? Here we have B that is just some symmetric matrix.
Not the determinant of the minor obtained by crossing out, no?
No. A and I and J going from 1 to n. This is just any symmetric matrix. Now the correct answer is that it is the element, the ijth element of the inverse matrix. Да. Да.
Скажите, пожалуйста, а вот мы определили вот это вот ожидаемое значение функции, когда она на R,
Да.
когда у нас на Rn.
Да.
Определение обобщается.
Да, определение такое же, да.
Так, а что такое этот... все, понял.
Все, вопрос исчез. Хорошо. Okay, so I'll try to prove that. And, well, the easiest case as before is if we take a diagonal matrix. And then we will try to make a change of variables to use this case in general. So if B is a diagonal matrix, B minus the inverse matrix is just 1 over beta 1, 1 over beta n. As I already told you, this case corresponds to n independent normal distributions. So in this case, xi, xj, for I different from j, is equal to 0. Maybe I should write it. Since the distributions are independent, this is just the mean value of xi times the mean value of xj. And this is equal to 0. While xi squared, the mean of xi squared is, well, xi is just an independent normal distribution with variance 1 over beta I. So in this case we obtain the correct answer. Now if I want to do it in general, I'll have to erase something. Right. So the integral of xi xj e to the power minus 1/2 bx x dnx. And again I assume that, well, I find the matrix P such that the transpose of P times B times P is this matrix beta 1, beta n. Okay, so here is the computation. This is equal to the integral of pxi, maybe I'll put here y to be clear, py j e to the power minus bpy minus 1/2 bpy py dny. Okay, this is just the change of variables where I go from the variable x to the variable y using this matrix P. Okay, this is equal to sum over k and l pki plj 1 over integral of yk yl e minus 1/2 beta y y. Let me call this matrix beta. Okay, so the ith element of py is the sum of pki times the kth element of y. And here I use the fact that p transpose times b times p is equal to the matrix beta. So I change this into this. And now now this is something I know. This is something I computed there. This is the simple case where beta is a diagonal matrix. So this is equal to sum over k. Well, first of all, I know that for k different from L this vanishes. So I only have to consider the cases when L is equal to k. And then I obtain pki, pkj, 1 over beta k. And this I can write it as P transpose beta to the power minus 1. No, sorry, P beta, yeah, okay. P transposed the element number ij.
that beta be a B?
Sorry?
The beta inside there, shouldn't that be a B?
No, this is beta. No, this is
It is diagonal.
beta is this diagonal matrix. Yes.
Okay.
Okay, so this is actually the formula for products of matrices, but then, well, with two complications. The first complication is that beta is a diagonal matrix, so the only coefficients are beta kk, which is here. And the second complication is that here I have to permute I and k. I would like it to be pik, so well, probably no. Well, it doesn't matter. So here I have to add a transposed matrix. Okay, and now from this equality you deduce that B is actually equal to P transpose power minus 1 times beta times P to the power minus 1. And if you compare this and this, you can see that this is precisely the inverse of one another. So this is the inverse of B ij. Okay, maybe the computation was too quick, or maybe it wasn't, but in any case it is not a very complicated conceptually. First you consider the case of independent distributions along the axis, and if the distributions are not independent along the axis, then you can always choose axes in such a way that they become independent by performing this change of basis P, and then you use the result you obtained for independent normal distributions. Okay. Yeah. Okay, but this is the complete answer for polynomials of degree 2. But now I would like to obtain the answer for all even polynomials, for all polynomials of even degree. So this is done by the following theorem called the weak formula. I will formulate it. Okay, so let us consider L1, L2k that are linear forms on Rn.
Degree of the polynomial.
2L will be, 2k will be the degree of the polynomial. The polynomial will actually be the product of these linear forms. In principle, I could have taken just the coordinates instead of linear forms, because every linear form can be decomposed as a linear combination of coordinates, but the theorem is true in this slightly more general setting, and I will use it as such. So let us formulate it like that. And I would like to compute the expectation value of the product of all these linear forms. So the weak formula says that this is the sum over all pairings. I will explain what this means. And for each pairing you take the product over pairs. And you take the expectation value LA, LB, where A and B is one of the pairs. So let me give an example, and probably everything will become clear. For example, the expectation value of L1, L2, L3, L4 is equal to L1, L2, the expectation value of L1, L2 times the expectation value of L3, L4, plus the expectation value of L1, L3 times the expectation value of L2, L4 plus the expectation value of L1, L4 times the expectation value of L2, L3. So hopefully this example explains both what is a pairing and what are pairs, but I will say it again. Here we have 2k linear forms. We have to divide them into pairs in some arbitrary way, something like that. And for each decomposition into pairs, we take the product over these pairs of the expectation value of the product of just two linear forms that form this pair. Yeah.
Pairs have to have different indices or not?
Yes, well, there are 2k linear forms, so there are k pairs.
Yeah, okay.
It is not a very clear question because among these linear forms you can have equal linear forms. This is not forbidden. So in this example there are 3 ways to divide 4 elements into 2 pairs, so yeah, into 2 pairs. So, well, this is the sum over the 3 subdivisions. So now I promised that I would compute this integral, square root of beta over 2 pi, integral over r, x to the power 2k, e to the power minus beta x squared over 2. Maybe someone can tell me the answer. This way we'll see if you have understood the weak formula. Maybe it's not completely obvious actually. So we have to divide x to the power, well, we have 2k linear forms, each of them is equal to x. So for every pairing, we will obtain the same contribution, expectation value of x squared to the power k. Now the question is how many pairings there are, how many ways to subdivide 2k elements into pairs, in k pairs.
The nomenclature is from 2k.
Now,
From 2k minus 2 over 2 and then divided.
Yes, I think this is the correct answer, but I have a simpler formula for it. It's 2k minus 1 double factorial. For the first x, you can choose its pair among 2k minus 1 elements. Let me erase this to start. Okay, so first you look at the first x and you want to choose its pair. You have 2k minus 1 possibilities for that. Once you have chosen the first pair, you look at the next free x and you want to choose the pair for it. You have 2k minus 3 possibilities. Then you look at the next free x and want to choose a pair for this one, and you have 2k minus 5 possibilities to do that. Okay, and so divided by beta to the power k. So this is the answer. And in the general case, since we already know the expectation values of polynomials of degree 2, the weak formula allows us to find the expectation value of any polynomial. Well, since I am in the mathematical part of the course, let me prove the weak formula. In mathematics, you are supposed to get proofs from time to time. Actually, I am not certain that I chose the best possible proof for. Well, the proof that I will tell you is not completely elementary because it uses the Fourier transform. But nonetheless, it is the simplest and the clearest one. So I decided that if you know the Fourier transform, it's definitely the best proof. And if you don't, then someday you will learn the Fourier transform and you will understand the proof. Okay, so the Fourier transform assigns to a function f in the variable x the function f hat of the variable y okay, so let me do it first in, I don't know. I think I can write it in general straight away. Integral over Rn of f of x e to the power I xy dnx.
So it's okay, they've learned the Fourier transform.
Yeah. Yes, this is the definition. So first you can, well, x is again a short notation for x1, xn. But as a first step you can look at it, well, you can consider the case of dimension 1. Then this is a function of one variable x. This is another function completely different of one variable y. And well, this function is defined by this integral. So it is the sum of some wave functions with different coefficients. For every period you have a different coefficient, and the coefficient is f of x. It is a sum of infinitely many wave functions with different amplitudes and different periods. And then you can go to the case of n variables. And if you are clever enough, you can see that if x belongs to an n-dimensional space, then y actually belongs to the dual n-dimensional space, because there is this product between the two. Or else you can consider that x belongs to r to the power n, and this is just the usual scalar product. And then you have these wave functions that go in all directions. In an n-dimensional space, when you have a wave function, it can go like that, or it can go like that, or it can go like that, and so on. And so we have a sum of all possible wave functions that go in all directions with all possible periods and with different amplitudes. Okay, so what do I need about this transform? First of all, the multiplication by xk, the operation of multiplication by xk is transformed into the operation of derivation with respect to yk. This is very easy to see, because if you have e to the power I xk yk, and then you transform it into xk times e to the power I xk yk. Or maybe I can write f of xk, f of xk. So as you see here, we multiplied the function f by xk, but you can also look at it here and see that this is just the derivative, sorry, this is k, the derivative with respect to yk. When you derivate with respect to yk, you see xk appearing here. The second property I will need, so this is actually a very simple property that you can understand even if you see this definition for the first time. Then there is a second property that I will need, which is that these functions I am using all the time, bxx, yeah. Okay, let me write it more to the left. It will look more beautiful. Is transformed into almost the same function, except that b is replaced by the inverse matrix. So this goes to e to the power minus 1/2 b minus 1 y y.
The determinant vanishes.
Sorry? Well, the determinant cannot vanish because it is a positive definite quadratic form.
It disappears.
Yes, the determinant disappears. This is not a very pleasant pleasant thing. There is a question of normalization, but this is how, yeah. This is how it works. And finally, yeah, okay, and this this is an exercise. This is also quite simple. Maybe I can give you an indication of how to do that on the other part of the blackboard. I won't do all the computations here, but it is something that you can do. If you take e to the power minus, let me do it in one variable, beta x squared over 2, and then you multiply it by e to the power I xy. Well, this is equal to e to the power minus beta x squared over 2 plus I xy. And now you can make a translation of x that kills this term. So this will be equal to, I'll try to do it correctly, x minus I over 2 beta squared over 2 y. Probably there is no 2 here.
There is no 2.
Yeah.
Because 2 is in the...
Yes, 2 is already here. And okay, minus and minus gives a plus. Yeah, so I have to subtract it back. Probably y squared over 2 beta, something like that.
2 beta squared.
2 beta, no, because there is a beta here. Well, I think it's right. I think it's right like that, but maybe, well, but if you do it at home, you will definitely find the correct answer. So now this is this is the integral that you can compute, and this is just a constant, e to the power. Yeah, probably I shouldn't do that later. Well, this is the Gaussian distribution that you know how to compute, and this is just a constant, e to the power minus y squared over 2b is a constant that you will put in front of the integral. And it is this constant in front of the integral that will give you actually the answer. This is the constant that you see appearing in front of the integral. Y squared over beta is beta minus 1, beta to the minus 1, y. This in dimension 1 is e to the power minus y squared over 2 beta. And this is where it comes from. Okay, and finally one last fact, which is the most difficult one to understand, so I won't explain precisely where it comes from. But if you taking the integral of f corresponds to taking the value at 0.
Is directly in the definition, isn't it? Or
Let us see. I think, no, it's not.
Integral.
Sorry?
What's under the integral?
Yeah, okay, f.
then the definition. Because you
Really? Ah, okay, yeah, okay, it's okay, it's difficult in the other. Yeah, okay, so it's.
in the other sense
Ah, okay, so that's easy. Okay, sorry. Thank you.
Y0, not x0.
At y equals 0. Yeah. Yeah. Okay, so now I'm going to prove the weak formula by making all the computations in the Fourier transformed part rather than for the function f itself. Well, it would be a pity to erase the theorem, so probably I'll try to do it here. Okay. Yeah, I don't have the proof here, so what shall we do? First of all, instead of taking linear forms, I will just take coordinates. I think you understand that it is equivalent. If this theorem is true for coordinate functions, then it is also true for linear forms. So we want to compute the integral over Rn. Let me see. We want to compute the following. We want to compute 2 pi n over 2 no, it's the inverse. Excuse me. Square root of determinant of beta of b, 2 pi to the power n over 2. Integral of x k1 x I1 xi to k e to the power minus 1/2 bx x dnx. And now I will transform everything by the Fourier transform. So here I have an integral that I will transform into the value at 0. Here I have multiplications by xi's that I will transform into derivations. And here I have this Gaussian function that I will transform into another Gaussian function. So this is equal to the value at 0 of the following: d over dy I1 d over dy I2k e to the power minus 1/2 beta minus 1 y taken at y equals 0. Right? Do you agree with me? I will underline the analogous parts. So this is what the Fourier transform does to my first formula. And now I will just stare at this and see what happens. What happens, so this is a quadratic form. You have e to the power some second degree 2 polynomial in y1, y2, and so on, yn. What happens when I compute the differential, the derivative of this with respect to yi2k? Well, it's clear what happens. The exponential remains an exponential, and here there are some terms ik something that descend in front of the exponential. Ik, let's say j, times the exponential. Now I compute the next derivative. Yeah, I have a question? Okay. Now I compute the next derivative. I have a choice. Either I can derivate the exponential or I can derivate the product that I have in front of the exponential. If I derivate this term, there is something I forgot. There is a yj here. So I can derivate this yj or I can derivate the exponential. If I derivate yj, well, then I will just obtain the coefficient beta minus 1 ik j. If I derivate the exponential, there is another way that is going down. I'm not sure. It's very clear. I'll have to. Yeah.
A small remark is that, in fact, what we've already got looks like a very good method of computation. Because even if we don't want to prove the formula, but want to compute.
Yes.
Basically, the derivatives S0 are called Taylor series. Taylor series of exponential is a very simple thing. So if you want to arrive to an answer in some particular case, it's already done. It's just to write out a Taylor series and to look for a coefficient.
Yes, that's true. So the weak formula actually gives you the Taylor decomposition of this exponential. Yes, you are completely right, but I will need the weak formula as it is. So let me do it again. Here we have some, maybe I can write it explicitly, beta minus 1 ij yi times yj. And now every derivative kills one of these yi's and puts yj here instead. And then the next derivative can make the same thing, kill one of the yi's and put a yj here, or it can kill the yi that is already here. So for every derivative there are two possibilities. And in the end, I want to take the value at 0. So in the end, I want everything here to vanish. Let's say this is the start. This is the middle. Here you will have some a well, I don't know, a1, a y3, y12 times beta minus 1 something times the exponential. And this is the end. Times the exponential. We start with just the exponential, then there are some factors in y that appear, but in the end all of them should disappear, because if at least one factor of y remains in front of the exponential, then the value at 0 is equal to 0. So how can it happen that all y's disappear in the end? First of all, for that we need an even number of derivatives, which we already know. Because one derivative puts a y here, the next one makes it disappear. And second, we need a pairing of these derivatives, precisely as I said. All derivatives go in pairs. The first derivative of the pair puts a y here, the second derivative of the pair kills it. What happens when we do that? There is a coefficient b minus 1 ij that remains. So all derivatives should be grouped in pairs, and for every pair we obtain a coefficient beta minus 1 sub ij. And this is precisely, well, this is beta minus 1 ij. So this actually both proves the first part, well, something that I have already proved, that the expectation value of xi times xj is equal to this coefficient beta to the minus 1 sub ij, and it also proves the weak formula at the same time. End of proof. So now I will start matrix integrals. Probably I won't have time to finish this time, so I'll finish the next time. So next time will be the continuation of matrix integrals, and I will also try to tell you about at least one ill-defined problems, because this is, in my opinion, the most interesting part about about problems inspired by statistical physics, that some of these problems are not well defined, but nonetheless physicists manage to solve them and obtain some very interesting mathematical facts that are quite mysterious for, well, even if you know the motivation, you still don't understand how it happens that it works. Okay, so I think I will erase all this. Yeah. Let me recall the definition of a Hermitian matrix. I will actually use absolutely no properties of Hermitian matrices, so if you don't know what it is, my definition will be completely sufficient. If it has the form, well, let's say Zij I and j going from 1 to n, let me put a capital N, not to be confused with the previous n. So Zij are complex numbers, and Zij is the complex conjugate of Zji. Another way to say that is that X transpose is equal to X complex conjugate. Okay, so it's not a symmetric matrix, but it is a matrix that is also almost symmetric. On the main diagonal you have real numbers, and in points symmetric with respect to the diagonal you have complex conjugate numbers. So now we will make a conceptual leap. Not a very difficult one, but you should be warned if you want to. Yeah. So the conceptual leap is to take what was my space Rn until now will now become the space of Hermitian matrices. Okay, so before, for example, I used the symmetric matrix B, a matrix of a quadratic form. So this will be a quadratic form on the space of Hermitian matrices. Well, the Hermitian matrices form a real vector space of dimension n squared. When you have a matrix, you must...
That can't be equal to bigger square.
Yeah. Yes, maybe the inverse notation would be better, but it's a tradition.
The notation is right.
Yeah, yes. So here you have n real parameters, because the numbers on the main diagonal are real. And here you have n times n minus 1 over 2 complex parameters. So if you add that together, you obtain n plus 2 times n minus 1 over 2, and this gives you n squared. Okay, so now I have to introduce a quadratic form, a positive definite quadratic form on this real vector space. Quadratic form so there is a very natural quadratic form on this space, which is the trace xy equals trace xy. So it is obviously a bilinear symmetric form. And to prove that it is positive definite, let us compute the trace of x squared. I have exhausted the water supplies and the erasers. But I have only 10 more minutes to go, so it doesn't matter. So let us compute the trace of x squared. The trace of x squared is equal to the sum over I and j from 1 to capital N, Zij, Zji. But these are complex conjugate numbers. So this is equal to the sum over y and j of Zij squared. So this is positive if the matrix is non-zero. Okay, 1 second. I think I economized more seconds than I wasted. Okay, so now excuses. An excuse, I will treat Zij as a basis of my vector space. Well, usually when you have a real vector space, maybe not as a basis, as coordinates rather. Usually when you have a real vector space, the coordinates are real linear functions on it, such that any linear function can be expressed as their linear combination in a unique way. Well, here instead you have linear functions that go from this vector space of dimension n squared to C. Okay, Zij are complex numbers, so this is a function that takes a matrix and that gives a complex number. They are linear. There is no sense to say that a linear function on this space is complex linear, because this is not a complex vector space. So they only are linear, even if they go into C. There are n squared of them, so that's the right number, that is the dimension of the space, and any R linear function L from R n squared to C is a linear combination of Zij, a linear combination with complex coefficients. Well, so it's not what you usually call coordinates, but it is really much simpler to treat them as if they were coordinates, instead of separating the matrix into a real part and an imaginary part. This would be maybe easier to understand, but all formulas become clumsier. So I will do it in this way. Okay, so this was my quadratic form B. Now I must compute its determinant and its inverse matrix in order to be able to write the correct integrals. So what is the determinant of B? Well, let me just write the matrix of B. Z11, Znn, and then you have Z12, Z13, and so on. So I will start with Zii and write all the other coordinates after that. Now maybe I'll do it. It's even better. Z12, Z21, Z13, Z31, and so on. So it's a bigger matrix. And here also I have the coordinate Z11, Znn, Z12, Z21, and so on. So the matrix is the following: 1, 1 here in this block, then there are small blocks 1, 1, 0, 0, 1, 1, 0, 0, and so on. And here it's 0 all the time. Right, because B is equal to sum of Zij, Zji. So if I is equal to j, I obtain just Zii squared, which are these ones on the diagonal. And if I is different from j, then I obtain these small 2 by 2 blocks. Okay, so the determinant of this matrix is equal to what's the determinant of this matrix? If you don't answer, that means that nobody is following.
-1 is minus 1 степень n на n.
Почти что. Определитель этой матрицы равен единице. А, нет, неправда, да? А, нет, неправда, значит...
Somebody is following.
Yeah, someone is following. Yes, that's good. Okay, so...
Четкость все в порядке.
Хорошо.
Тоже четкость.
Четность чего? What is that? No, the... Okay, and what is the matrix B to the minus 1? Well, again, I can write the inverse matrix of every block.
It's not the same.
And obtain, well, it's just equal to B. Right, this is true, there is no mistake in science this time. Because the inverse of the identity matrix here is the identity matrix, and this matrix squared gives you 1. So the expectation value of Zij, Zji is equal to 1, while the expectation value of Zij, Zkl is equal to 0 in all other cases. Right? Okay, so this is the time to end. Okay, so then...
You have...
No, it's a good time to end. So the first problem we'll consider next time is to evaluate the expectation value of trace of x to the power k. So x is the Hermitian matrix, and we can... So this is a polynomial in the Zij's of degree k. Well, as I said, for odd k it will vanish, but for even k it will give some interesting answer. And our first problem will be to find this expectation value. That's all. I think it's precisely 1 hour and 14 minutes.